intermolecular forces is a very important concept to understand. And the reason why it's so important is because we would not have the liquid phase or the solid phase in the universe without intermolecular forces. Okay, intermolecular forces are what is the glue that holds matter together. If there was no intermolecular forces, then these things would be separated and we would see them as gas, in which there should be minimal interaction between one particle and another. So here on this planet Earth, we are subjected to conditions of temperature, pressure. And so we have to pay attention to those conditions in order to understand the properties of matter based on the intermolecular forces phenomena. So let me go ahead and get started on that. And again, this is a review just so that you guys can catch up on the topics that we're covering. Okay. Um, you guys should be able to uh, draw in your mind, or at least visualize in your mind, the following concept. What are ionic bonds? Okay. It has to do with the atoms that make them up. What are polar covalent bonds? Again, the atoms that make them up and their attraction for electrons, because remember, bonds are made through the sharing or the transfer of electrons. Dipole-dipole interaction. What exactly is a dipole? And how do we visualize a dipole? Hydrogen bonding. What is hydrogen bonding? And in this review, you guys will see exactly what that is. London dispersion force. These right here are concepts that you need to know in order to understand intermolecular forces. Okay, so let's start with a heating cooling curve. And the reason why we need to do that is because, again, the conditions by which matter is exposed to will dictate the amount of intermolecular force matter will experience. And the amount of intermolecular force matter experience dictates the phase of that particular item. So if we take water, and water is a classic example because, of course, it's ubiquitous and it's everywhere, but you can take carbon dioxide, you can take some other compound, and you can do the same thing. Of course, it's going to be subjected to different conditions because of the atoms that make it up. But water is a good example because, again, it's something we deal with, especially in this particular course. If you take, say, 1 gram of matter, 1 gram, okay, and change, and we're going to put it, expose it to 1 atmosphere pressure and vary the condition, then we can change the phase. If we lower the temperature below 0 degrees Celsius, then there's enough intermolecular force to bring the water molecules together so that it doesn't displace itself. And what we have is the solid phase. And so that's what you have right here. You have 40 degrees, minus 40 degrees. And what we have is right here, the solid phase. Okay. Now, the phase of matter, phase of water does not change when you put in energy. And as you put in energy, what happens is that the molecules of water starts to vibrate. In fact, the molecules of water starts to vibrate at any temperature above 0 Kelvin. Okay, it's just that it's vibrating very slow near 0 Kelvin, like 1 Kelvin, and then it vibrates much more vigorously as you raise the temperature. Well, as you raise the temperature all the way to 0 degrees Celsius, what happens is that the vibration of these water molecules is so large that they start to break apart. And what we have here is the melting point of ice, or melting point of water. And what we have is an equilibrium. This is an equilibrium. And the reason why it's called an equilibrium is because both phases, solid and liquid, coexist and they're interacting. Some solid goes into the liquid, some liquid goes into the gas. And that's because when water melts, the temperature is constant. That's why you see this line that goes horizontal right here. Okay. Let me change my pen. That's why you see this line that goes horizontal right there, because the temperature doesn't change, but the energy that you're putting in is causing the bonds to break and causing the solid to melt. Okay, and so it's a coexistent. Now, when the last crystal melts, then and only then does matter starts moving faster and the liquid starts to have a higher temperature, at which point you're not at the solid liquid equilibrium anymore, you are pure liquid. Now, this point in this phase diagram is water at 0 degrees, pure water at 0 degrees. This point in the phase diagram is solid ice and liquid water in coexistent 50%. This point in the phase diagram is solid ice at 0 degrees. You can have solid ice at 0 degrees and solid and liquid water at 0 degrees, depending on where you are in this diagram. Okay, and of course, as you move along this diagram, the amount of ice and the amount of liquid water is going to change in their ratio as you add more energy, or as you remove more energy. This is the removal of energy right here. Okay, so when you start adding energy, the liquid water starts to vibrate more. Of course, in the liquid phase, you can put an object through it because they'll move out of the way. Okay, that's why things can be immersed in water, whereas in solid ice they can't, because the water molecules are stationary. They're not going to move out of the way. But when you hit 100 degrees Celsius, then what you have is you've added enough energy to break down the intermolecular forces of water so that now they totally separate. And now they're not clinging onto each other anymore. They're actually separated. And what you get is the steam or the gas phase. And that's what you see right here. This is a liquid gas equilibrium. They coexist. When you're boiling water, what happens is that there's liquid and steam in that container at the same time. That's what we have right here. It's an equilibrium. We're going to study equilibrium in more details in chapter 15, but know that you've already been exposed to it in phase diagrams. Now, right here, you have liquid water at 100 degrees. Here you have vapor, steam at 100 degrees. Anywhere along this line, you have different ratios of liquid and gas. Okay, and as you add more energy, of course, then more of the liquid will convert to gas. In fact, if you have 1 gram of water, it'll take you 540 calories to take the liquid water at 100 degrees and convert it to gaseous steam at 100 degrees. Okay, that's the amount of energy that you need. Over here, it takes 1 calorie to raise 1 gram of water 1 degree. Okay, that's the specific heat of water. It takes 1 calorie to raise 1 gram of water 1 degrees. Of course, if we want to raise 1 gram of water 10 degrees, it's going to cost 10 calories. If we want to raise 10 grams of water 20 degrees, it's going to be 10 times 20, 200 calories. So you can see why I like to use calories in these phase diagram, because it's easy to compute in your head. Okay, if the question is about joules, then just remember that 1 calorie equals 4.184 joules, and then you can make that conversion. Anyway, let's go back to this phase diagram. Once you have gaseous steam and the last drop of liquid has been converted to steam, then any energy that you put in is going to cause superheated steam, and that's water vapor is going to move faster. Okay, it's going to move faster, and what you have right here is pure gas. So this is a heating cooling curve, and these values right here are the amount of energy that you need to convert 1 gram of water through these different phases. Okay, if you want to convert 1 gram of water from solid ice to liquid water at 0 degrees, it's going to cost you 80 calories. If you're going to raise the temperature of 1 gram of ice from, say, -10 to -9, it's going to cost you 0.49 calories per gram per degree. So that's how you read this phase diagram. Okay, remember that melting and freezing are the same thing in the reverse order, and the heat that is associated with that is called the heat of fusion. Remember that boiling and condensation is the same thing. Okay, and the energy associated with that is called vaporization. So hopefully that is a good summary or a summary of what you guys learned already in the past. This is what we call a heating cooling curve. And the reason why matter has different phases is because of intermolecular forces. The reason why matter can be bonded together and you get different compounds is because, sorry, this is intermolecular force. The reason why you have different bonds and you have different compounds is because of intramolecular force. Okay, so what's the difference? Intramolecular forces are the sharing of electrons, either the transfer or the sharing of mutual electrons to cause bonds. Intermolecular force, on the other hand, is the interaction from one chemical to the other through space. Okay, through space. So it's between chemicals, not within chemicals. Now, in terms of intramolecular, you guys should remember there are two types. There's ionic bonds, and then there's electron sharing. And electron sharing, you have something called covalent bonds. When the electrons are equally shared, you have covalent, pure covalent. When they're not equally shared, it's called polar covalent. And that's because one atom has a bigger electronegativity, is more stingier for electrons than the other, and so it's going to hoard more of the electron density. And so what that does is it causes the electron cloud to shift to one chemical versus the other, and that results in a polar. Think of polar in terms of the magnets. When you have magnets, you have a north pole and a south poles, and one side is, say, positive and negative. That's the same thing that happens to a molecule. When one side of the chemical hoards more of the electrons than the other, then that side is more partially negative than the other, and the other is more partially positive. That causes a phenomena like a magnet in which you have poles, opposite or differential of charges throughout the same entity. Okay, so in terms of intermolecular force, there's more, hopefully, that you guys covered. There's something called ion or ion dipole. We're not going to be so concerned with that. We're just going to be looking at the four main intermolecular forces, and these are ion dipole. Ion dipole is the whole reason why sodium chloride dissolves in water, okay? And that's because sodium chloride, you guys know, is NaCl, and when it goes into water, it breaks up into its ions because the ions are stabilized by the water molecule, and water is a polar chemical. So that's an example of an ion dipole type of intermolecular force. Dipole, of course, are when chemicals that are polar come together. What happens is that the chemical themselves interact like magnets, where you have positive and negative, and then here's another chemical, the negative and positive, and so the opposites will attract, and what we have here is dipole-dipole interaction. So they arise from polar molecules. If the chemicals are non-polar, that is, they don't have a dipole, something like helium or xenon, they don't have a dipole, or maybe fluorine, that molecule, where the electron sharing are mutual, then there's no distortion in the electron cloud, and so those chemicals do not have a dipole. If you have carbon monoxide, on the other hand, oxygen is more electronegative than carbon, and so it's going to be hoarding, it's going to be attracting more of the electron density on itself. And because it has more of the electron density, then we have something called a polar chemical, and polar chemical gives rise to dipoles. Okay. Then we have dipole-induced dipole, and dipole-induced dipole is the way oxygen would dissolve in water. Oxygen itself is nonpolar. The reason why it's nonpolar is because you got two oxygen atoms. They're attracted for the same set of electrons, and they have equal strength. And so the electron cloud is not distorted in oxygen. And yet, without oxygen dissolving in water, we would not have marine life. Okay, so how does a nonpolar molecule dissolve in a polar molecule? Well, it's through dipole-induced dipole. Okay, that's the intermolecular force responsible for that. So you see, intermolecular forces explains a lot of phenomena that we just take for granted. Okay, induced dipole. This right here is pretty important because it's basically what all matter contains. All matter contains electrons, and electrons, if you take xenon, for example, it has an electron cloud. And every once in a while, under the right conditions, especially low temperature, the electrons are going to bunch up. Okay. And when it bunch up, this part of the atom, or this part of the nonpolar, because this is especially true for nonpolar, but it's also true for polar chemicals, because polar chemicals have electrons. But this part of the chemical will have more negative than this side, which is lacking, and that'd be partially positive. Well, what that does is that a nearby xenon atom will recognize that this part is lacking electrons, partially positive, and so all the electrons are going to bunch into that side, and that side now becomes partially negative. And so what you have is a cascading of these effect, and it's like the wave, if you ever gone to sporting events where it just, someone gets started and then it gets the whole crowd going, and what you get is the wave around the stadium. Well, this is the same thing. Under the right conditions, one of these chemicals will have an induced dipole. That's because, or it's going to have a dipole, and then it affects its near neighbors. So that in a summary is how we would explain induced dipole or London dispersion force. And I forgot to put one more in here, and that one happens to be hydrogen bonding, which is really important for water. Okay, so again, these are the relative strength, but don't think of it as black and white. Some induced dipole can be stronger than dipole, even though the range is going to be wider. You can see that the range is between 0.04 kilojoules to 40 kilojoules. So some chemicals can actually overcome the dipole interaction of some matter. Whenever you have a solid phase at ambient condition, like iodine, then iodine, remember, is nonpolar, and yet at room temperature, it's a solid. That means there's a lot of intermolecular forces in play here. Why is it a solid at room temperature? Because iodine atoms are huge. And the bigger the atom, the more electrons they have, the more likely they'll have a London dispersion force as the main mechanism for its intermolecular force. So you can see here that for intermolecular force, it's not black and white. What you have is overlapping, okay? But in general, London dispersion force are the weakest. Dipole is going to be stronger than that. And then hydrogen bonding, which isn't here, is probably the largest. But again, some London dispersion force can overtake hydrogen bonding. Okay, it depends on the chemical that you're working with. It's on a case-by-case basis. It's not black and white. That's why chemistry is so difficult, because you can't just take a rule and apply it across the spectrum. You have to look at it on a case-by-case basis, because there's so many exceptions. If you remember the rule in general, it'll get you through probably 85% of the conditions, but it's that last 15% that they'll probably put in the exam. And if you don't know the exceptions, you're going to get that problem wrong. So to be really knowledgeable on these weird exceptions, you got to be taught why these things occur. And hopefully you get that throughout the course that you're taking. Anyway, let's move on. Again, intermolecular forces are important because they manifest, the intermolecular force manifests its phenomena on the properties of the chemical that you're looking at. Again, let's take a look at water. Okay, when you take a look at water, what you find out, water is H2O. It has a molar mass of 18.0 AMU. It's one of the lighter chemicals and it's one of the smaller chemicals. And so you would expect, for the fact that there's not a lot of electrons in there, that the intermolecular forces would be weak for water. And yet it has one of the higher boiling points for very low molar mass chemicals. And why is that? Well, it's because not only is water having electrons, but it's polar. Okay, the oxygen is more electronegative than the hydrogens, and so it's going to hoard more of the electron density towards the oxygen, which makes it a polar chemical. But on top of that, because it's the oxygen, which is very electronegative, is bonded to a hydrogen, then it takes advantage of poor little hydrogen and basically draws almost all the electron density onto itself. That exposes the proton on hydrogen, which is now susceptible to another electronegative element, like another oxygen from a nearby water molecule. That interaction right there is hydrogen bonding. And because water can hydrogen bond, it adds an extra glue that chemical will have to basically pack it together, to make it glued together to another water molecule with exceptional strength, and you need higher energy to break them apart. So that right there gives is the reason why it has a very high boiling point. It also has a very high melting point. It has a high heat of vaporization. In other words, you need a lot of energy to get it from the liquid state to the gas state because you're breaking the interaction between them. It has a high heat of fusion. You need a lot of energy in order to get it from the solid state to the liquid state. Remember, fusion is melting. Okay, it has a high heat, specific heat and heat capacity. In order to make these chemicals move faster, okay, then you need more energy. Remember that the heat capacity is going to be the when you have a solid, how much energy you need in order to raise the temperature. Specific heat is going to be the amount of energy you need to raise that substance 1 degree basically Celsius. It's going to have a high surface tension, a strong capillary action. It's going to be viscous, especially for the fact that it's a light chemical. It's not as viscous as molasses, but molasses, it has a very large, it's made up of different chemicals, and those chemicals are huge, which means that there's a lot of dipole-dipole interaction. There's probably even some hydrogen bonding involved in there. And then it has a very low vapor pressure, okay, or very high vapor pressure. No, sorry, low vapor pressure. All these are high for water, high boiling point, high specific heat, high surface tension, except the vapor pressure is actually low. It's opposite. And that's because you got to understand the definition of vapor pressure. And we'll talk about that shortly, okay? So a little bit of review about polarity. Polarity is not only involved when you have a binary chemical, and that's when you have X bonded to Y, then all you have to do to determine if that chemical is polar is look at the electronegativity difference. And if one chemical or one element is more electronegative than the other, then it's going to be polar, okay? But suppose you have a chemical in which you have say BHFF. Okay, well, there, what you would need to do is you recognize the fact that, again, the fluorines are more electronegative than the hydrogen, and so it's going to be drawing the electron cloud away from the boron. And so again, you get a polar situation. But how about something like ozone? You guys hopefully remember the Lewis structure of ozone. Ozone is O3. Okay, ozone is O3. And yet that chemical is polar. And the question is, well, they all have the same atoms in its makeup. How could it be polar? The reason why it's polar is because hopefully you guys recognize that this is a bent chemical. And because it's bent, what you have is a situation where the two oxygens in the end are pulling on this one oxygen with different strength. And so you have a distortion on the electron cloud. That's the key to understanding polarity. If there's a net distortion in the electron cloud, then that means one part of the chemical is going to have more electron density than the other. And when you have that situation, then the chemical is polar. That's why ozone is polar, is because even though the atoms in ozone have the same electronegativity, it's distorted because of its shape. That's why you need to know not only the identity of the atoms that make it up, but also the shape, the Vesper shape, the molecular geometry of the chemical, if you really want to pinpoint the polarity of a chemical, okay? Because if you take a look at carbon dioxide has carbon, oxygen, and oxygen. And yet the atoms within carbon dioxide are different. Carbon has a different electronegativity than oxygen. But what happens is that it's linear. And so what happens is that the electronegativity between the oxygen, because they're pulling the electron cloud away from carbon, negates themselves. So if you didn't know that it was linear and you thought it was bent, then you would think carbon dioxide is non-polar. Sorry, you would think carbon dioxide is polar because of the fact that it has a distortion on the electron cloud. But that's not true because carbon dioxide is linear. And so the pulling of the electron density away from the carbon are going to be equal but opposite. So hopefully you guys remember that in Chem 200 or Chem 152, because the way you want to determine whether a chemical is polar or non-polar is, one, look at the atoms that make it up, look at their electronegativity, and look at their molecular shape. Remember I told you that elements that are electronegative are going to be hoarding the electrons. And so if you have something like carbon monoxide, you know it's polar because oxygen has an electronegativity of 3.5, carbon has an electronegativity of 2.5. And so that means that the electron density is going to be pulled more towards the oxygen. In fact, you don't even need to know the electronegativity value to figure out whether a chemical is polar or not. The most electronegative element is fluorine, and the electronegativity increases towards fluorine. So if you take a look at two atoms in the periodic table, let's say that we have oxygen and carbon, and let's say that we have carbon, oxygen, and nitrogen. And I ask you, which chemical is more polar, NO or CO? Well, the difference in electronegativity is going to be bigger for CO because they're further separated in the periodic table, which means they have a bigger difference in electronegativity than NO. So the answer there would be CO would be more polar than NO. So the bigger the separation between the atoms in the periodic table, the bigger the difference in electronegativity. This is for binary chemicals now where there's two atoms. That difference in electronegativity makes it more susceptible to being polar. Okay, so again, I just want to point that out. Nitrogen, oxygen, fluorine, and chlorine are your most electronegative elements. Whenever hydrogen is bonded to those very strong electronegative elements, what we get is something called hydrogen bonding, okay? Chlorine is mentioned there just because if you take a look at, let me erase this, okay? Chlorine is mentioned there because you can see that chlorine has the same electronegativity as nitrogen. They're both 3.0, but it's not as, it's not, its influence on electronegativity is not, its influence on polarity is not as huge as nitrogen. And that's because chlorine's bigger atom. Because it's a bigger atom, when another electron tries to come into chlorine, it's further away from the protons. Remember, the protons are the ones that are attracted to the electrons. So that attraction isn't as efficient as nitrogen, in which the core, the valence electrons are closer towards the nucleus. And so it's much more efficient in terms of, say, hydrogen bonding than chlorine is. But again, chlorine is in there because it does have an electronegativity of 3.0. Here's an example of dipole-dipole interaction. Here, all of these are nonpolar, and yet their boiling point goes up as the atom becomes bigger. And that's because it's not the polarity of the chemical that influence their boiling point. It's actually the number of electrons that that chemical has. Bromine is going to have more electrons than dinitrogen. It's going to have a higher boiling point. On the other hand, if you look across here, these all have the same, about the same molar mass. And yet, if we take a look at the boiling point of these guys, these will always be larger than their corresponding nonpolar chemical because of dipole interaction. Okay, they're always going to be bigger. Minus 62 is higher than minus 90. 97 is higher than 59. The fact that it goes up, going down is because the atoms become larger. So you have two things at play: the polarity of the chemical and then the size of the chemical. Here are nonpolar chemicals, okay? And you can see that this explains what we call London dispersion force. London dispersion force, as I told you earlier, is the fact that you have a polar chemical in which the electron bunch up to one side, and that causes its neighbor to be attracted to one side of the chemical to a greater degree than the other, and you get this wave that comes in. And when you have low enough temperatures, what occurs, of course, is the attraction of one chemical to the other, and what you get is either the chemical turning to a liquid or the liquid turning into a solid. That's London dispersion force. But it's going to be biggest for those chemicals with the larger amount of electrons, because it's the electrons polarization, the way the electrons are being able to go to one side of the chemical, that dictates the size of the intermolecular force that you're observing. In this case, we're looking at boiling point. Okay, so you can see that xenon, which has more electrons than helium, is going to have a higher boiling point. Iodine has a boiling point of 457 Kelvin. Okay, remember that the boiling point of water is 373 Kelvin. Okay, the freezing point of water is 273 Kelvin. This thing, it has a higher intermolecular force. The boiling point is higher than water. Water is 373, 100 plus 273. Iodine's 457 if you want to boil it up. Of course, what happens is that if you ever played around with iodine, or if you ever watch iodine, is that it'll go from the solid to the gas phase under room conditions. And that's because there's something else at play there. Okay, but if you want to heat it up and you want to get into the liquid phase, then it's going to cost you 400. It's going to be 457.6 kelvins to do that. So this is London dispersion force. Now we look at this chart right here. And this chart kind of shows you what happens to the boiling point of different compounds as you change their molar mass. Here we have methane, tetrasilane, geranium tetrahydride, tin tetrahydride, and you can see that the boiling point goes up. And the reason why is because all of these are nonpolar, but tin is a bigger atom than carbon. The bigger atom means that it's got more electrons. Its London dispersion force is going to be bigger than CH4. Same thing here, H2S, H2SE, H2TE. Now, you guys know that these are all in the same family. Carbon, silicon, germanium, tin are all in the same family. The sulfur, selenium, this selenium, tellurium are all in the same family. The next element above sulfur is oxygen. Okay, and so what we have here are these again. This phenomena shows you why these chemicals have higher boiling point. But when we get to elements in the first row, what happens is that their boiling point really dramatically goes up, as you can see in this slide. And the question is, why are these things having a higher boiling point than predicted? The boiling point would be predicted to go down in most of these chemicals, but it actually goes up. And that's because of the hydrogen bonding phenomena. Okay, the hydrogen bonding phenomena. So hopefully you guys remember that from your general chem or chem 152. Yeah, there's a question about sublimation. Sublimation is, if you ever seen dry ice, okay, dry ice is a solid under normal conditions, and yet it doesn't go into the liquid phase like what ice does. It actually goes into the vapor phase. Same thing with iodine, okay? When you have iodine and you have crystals of iodine, then it doesn't melt. It actually goes into the gas phase directly. And that's because of the phase diagram that we'll cover shortly. But the phenomena when a solid goes into the gas is called sublimation. When a gas goes into, sorry, that's a solid. When a gas goes into the solid, it's called deposition because it deposits. You do that a lot in the silicon industry. But those are what we call these different phase changes phenomena. Okay. Let's see. The problem with dry ice, if you want to keep things too cold, is that the temperature is so cold. It doesn't make, remember that when you freeze things, especially for food products, it's made out of water. And when you freeze things, the water will freeze. And then the problem with water is that when it freezes, it also expands because it wants to maximize its intermolecular force. And so when the water expands, it ruins that particular product. And so if you ever freeze vegetable or you try and put it under conditions of dry ice, then what happens is that you could ruin it because the expansion of the water in those vegetables or that content is going to make the integrity of that substance break down. It's going to expand and then ruin it. What you want to do is you want to keep it cool, but not freeze it. Okay. Yeah. So think about that. If your refrigerator ever goes out and you need it to be maintained at a certain level, then dry ice is a way to maintain it. But don't trying to make sure that and dry ice, I don't think will ever lower the temperature unless you really isolated it, in which case it will cause that water to freeze in whatever substance you have. And then as it freezes, the water will expand. And depending on the product that you have, it can ruin it. Of course, some items that needs to be frozen are okay, like frozen vegetables. But if you want to keep it fresh, then Try not and freeze it. Keep it cool. Of course, the shelf life is not going to be as long, but keep it cool. And one of the ways to do that, of course, is like dry ice. And that's because when it disappears, it doesn't leave a residue behind. It just escapes to the atmosphere. Okay. So let me go ahead and move along here, because we're coming up at 5:40, and I really want to get through this and then talk about concentrations. So a lot of these things, let me just clear my sheet here. Oops. Okay. Are things that hopefully you guys remember. Hydrogen bonding is really important for those of you who want to be doctors, in the future, because our biological integrity, the proteins that make us up, the DNA that is our genetic code, is based on hydrogen bonding. The way DNA sort of, the base pair comes together and unwinds in order to replicate itself, is based on hydrogen bonding. So there's a lot of examples of where hydrogen bonding really plays an important role, not just because it changes the property of matter, but because it causes these phenomena that we didn't know about 100 years ago to as the reason why life as we know it exists. So again, the base pairs are based on hydrogen bonding. Proteins are based on hydrogen bonding. And if you take more biology courses, you'll see where hydrogen bonding plays a central role. So if I give you a question like this is a review question. You guys should be able to recognize which chemicals have hydrogen bonding. Whenever you see an OH, we call that a functional group in organic chemistry. Whenever you see that in a compound, you know it has the capability of hydrogen bonding. What you need to do is you need to find hydrogen bonded to either fluorine, oxygen, nitrogen, or chlorine. If you see that in the structure, then hydrogen bonding occurs. If you just see hydrogen and fluorine, but they're not bonded together, then there's no hydrogen bonding. They have to be directly bonded together. So this has no hydrogen bonding. This has an OH that has hydrogen bonding. That has an OH that has hydrogen bonding. Hydrogen bonding. Here you have NH. So that has hydrogen bonding. Here, there is no hydrogen bonding because even though you have oxygen and hydrogen, they're not directly bonded together. You have one of the two conditions for hydrogen bonding. That is, you have an electronegative element. Two of the three conditions, I mean. You have electronegative element, you have hydrogen, but you don't have the third condition in which that electronegative element is bonded directly to the hydrogen. So that's not hydrogen bonding. This is not hydrogen bonding, and this is definitely not hydrogen bonding. Okay, so you should be able to recognize which chemicals can have hydrogen bonding involved. Again, it has to have one of these electronegative element directly bonded to the hydrogen. Okay. So these are the answers. Let me clear my. Okay. So likewise here, you guys can look at this and tell me what type of intermolecular force a chemical have. By the way, if a chemical has electrons, then they always have London dispersion force. All matter will have London dispersion force because electrons are going to be in there. Then what you need to do is look for which chemicals are polar. This is polar, this is polar, this is non-polar. Why? Well, this is actually polar because of its bent. This is polar and this is polar. Okay. The reason why this is polar is because oxygen you have to know the molecular geometry, and it's bent. It's bent like water. So all of these are polar. Now, which has hydrogen bonding? This is hydrogen bonding. This has hydrogen bonding. Those are the two. Whenever a chemical has hydrogen bonding, it's also polar and also has London dispersion force. You're going to check mark all three. And then, of course, we know this from that. So this is non-polar. This is polar, 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 polar. Okay. The only chemical in here that's non-polar is going to be ethane, because that's totally symmetric. So you can see that in the answer. Okay. Again, hopefully this is a review, but if it's new, then hopefully I'm jarring your mind so that you guys can remember this. So this is just a summary of intermolecular forces. Okay. This is some of the properties of intermolecular forces. Okay. This is the heating cooling curve, but now I want to relate it to something called the phase diagram. In the phase diagram, what you have is here, it's under constant pressure. You're at 1 atmosphere, but you vary the temperature. Here, you vary pressure and temperature. This is the temperature line. This is the pressure line. So under pressure, a different pressure and temperature, you have matter existing at a certain phase. So here we have the solid phase. I'm going to clear my. Here we have the pure solid phase. At a certain pressure, at a certain temperature, you're going to have solid. Below that, you're going to have a gas, okay? And you don't have a liquid existing at that. This is for water now, okay? If we are at 1 atmosphere and we change the temperature, what happens is that 1 atmosphere and we start to raise the temperature, then we get that solid melting. So right here, we're raising the temperature. This point in this phase diagram actually corresponds to this line, because here you're getting the solid converting over to the liquid. You get the solid converting over to the liquid. Then once you put in enough energy, remember that the phase change happens at constant temperature. So that's why you're at one line. This is constant temperature right here. Now, when the last crystal melts, then the temperature increases, and what you have is liquid. And that's what you see right here. And then we have a phase change again, but it's at 100 degrees. That's this line right there, or that point right there. When the liquid converts to a gas, it happens at one temperature. Then when all the liquid has converted to a gas, then will the temperature increase. So that's how you relate this particular phase diagram to the heating cooling curve. These equilibrium are going to be these points in the phase diagram. And then depending on the pressure, you can get water again going from a solid to a liquid to a gas. Now these lines right here is what happens when you take water and you put some sort of contaminant in it. Okay, we're not going to be looking at that, but it's something called colligative property. If you take pure water and you add salt to it, the freezing point of that salt water is not 0 degrees anymore. It's actually going to be lower than that. Okay, it's going to be lower than that because of the colligative property. So let me clear this real quick. So that's what would happen to the freezing point if you put some sort of contaminant in your pure water. Okay, what happens if you put salt in water? Like suppose you're cooking, you have water right there, and you throw in a dash of salt. What will happen is that the boiling will stop, and that's because the boiling point has been elevated. Again, it's a colligative property. You can read about the fact that now the water molecules are going to be shielded from the surface, and so you need more energy, higher temperature, to cause that water molecule to escape the surface, and so the boiling point increases. So you change the properties of your water because now it's contaminated by some sort of particle. That's why you put antifreeze in your radiator, because it elevates the boiling point. It's called antifreeze because it depresses the freezing point so that your radiator or the water in your car doesn't freeze over. It depresses the freezing point and it elevates the boiling point. Those are colligative property. And you guys sort of covered that, hopefully, in chapter 11. If not, then it's something to keep in mind. Yeah, exactly. When you boil eggs, you put a little salt. The temperature of the water is actually higher, okay, than 100 degrees. So because of boiling point elevation. This is a Maxwell-Boltzmann distribution plot. And the reason why we need to know this a little bit is because, well, you're going to see this in equilibrium as well. But what happens here is if you have, say, water chemical, do this, H2O, or any other chemical, say at 20 degrees Celsius. I think I talked to you guys about this a little bit. And you have, say, 1 mole of water, 1 mole, 6.02 times 10 to the 23rd. But that 1 mole of water, let's not make it 20 degrees. Let's make it 200 degrees because we're looking at a gas here, okay? That 1 mole of water gas is going to have different particles are going to have different energy. Some of them are going to be moving slower. Some of them are going to be moving faster, okay? And that's because of the fact that we have something called the Maxwell-Boltzmann distribution. They don't all have the same energy, but they do have a average energy. Now, if you raise the temperature higher, more of it's going to be shifting over to higher energy. And that's what this Maxwell-Boltzmann distribution plot shows you, okay? It also explains why it basically is something that you guys remember when we talked about the root mean squared in gas laws. But I wanted to throw this in here because you will see it again in equilibrium, okay? And here what we see, of course, is the different type of temperature and vapor for different substance. You guys will see this in experiment number 7. What happens is that at a certain temperature, then the vapor pressure is going to increase. And that's just part of the phase diagram, okay? So this, again, is chart that you see in chapter 11 that shows you the different properties of matter under different conditions, okay? So here, again, if you want to take, for example, a chemical like ethanol, and you want to know its boiling point, then you use this diagram. This diagram tells you that at 1 atmosphere, which is when ethanol will start boiling, you can figure out exactly what temperature you need to apply in order for that ethanol to start boiling at 1 atmosphere. And here you can see that here is the, this is for water, but for ethanol, which is this, then it'll start boiling at 80 degrees. If you have diethyl ether, then it'll start boiling at about 35 degrees. For water, which is this, then the boiling point is 100 degrees at 1 atmosphere. If you don't have 1 atmosphere, you have it under vacuum, for example, and let's say that you have it at not 760 millimeters of mercury, but 400 millimeters of mercury, then you can cause that water to boil at minus 80. That's why if you ever take water and you put a vacuum, you actually start to see that water start bubbling. And that's the boiling process. You're actually causing the water to boil at a lower temperature because you've reduced the pressure. Okay, you've reduced the pressure. So again, this phase diagram just sort of explains these little diagrams that you see here in one chart. Okay, in one chart. So I'm going to finish up with that, and I want to go into, at least in the next 15 minutes, some concentration discussion. And